Hey science and technology lovers! Welcome to a video that will literally change the way you see the world around you. Today we're exploring GPS, the Global Positioning System. You probably think of GPS as the thing that guides your phone or car, but in reality, GPS is a mind-blowing combination of satellites, Einstein's relativity, atomic clocks, and ingenious engineering. Smash like, subscribe, and comment below. Has GPS ever saved your day or gotten you hilariously lost? Let's dive in! What is GPS and what is it for? GPS, Global Positioning System, is a network of satellites and ground stations that allows anyone to determine their exact position, speed, and time anywhere on Earth, often within a few meters or even centimeters. It was originally a secret military project by the USA, but today GPS is free and available to the whole world. On your smartphone, in your car, drone, watch, tractor, and even in scientific equipment. Thanks to GPS, we can navigate cars, ships, planes, and hikers, synchronize banking transactions, electric grids, and stock markets, measure time and position with extreme precision for science and industry, find lost phones, track shipments, manage logistics, guide precision agriculture, construction, and surveying. The history of GPS, from Cold War to everyday life. 1973. The U.S. Department of Defense launches the Navstar GPS program, originally as a guidance system for missiles and military navigation. 1978, 1985. The first GPS satellites are launched only for military use. 1995. GPS becomes fully operational with 24 satellites. The first civilian receivers appear, large, expensive, and slow. 2000. President Bill Clinton ends selective availability, intentional signal degradation for civilians. GPS becomes accurate and global. Today, GPS is everywhere. Phones, cars, wristwatches, drones, and millions of devices. With advanced corrections, RTK, DGPS, positioning can be accurate to a few centimeters. The architecture of GPS 3 Systems Segments GPS consists of three main components. The space segment, GPS satellites. There are at least 24 active satellites, usually around 30, orbiting Earth in 6 orbital planes at 20,200 kilometers altitude. Each orbits the planet twice a day. Every satellite broadcasts radio signals with a unique identifier, an extremely accurate time from an onboard atomic clock, current position, ephemeris data, system status. The control segment ground stations, a network of monitoring stations and main control centers worldwide. USA, Hawaii, Ascension, Diego Garcia, Kwajalein. They monitor, correct, and update satellite orbits and synchronize the atomic clocks. The user segment, GPS receivers, your smartphone, car navigation, drone, smartwatch, GoPro, farm equipment. Receivers pick up signals from multiple satellites at once, ideally 4 or more. The principle of GPS, trilateration, not triangulation. GPS positioning is based on trilateration, calculating your location based on distances to several satellites, not by measuring angles. That's triangulation. How does a GPS receiver find your position? Every satellite transmits the exact time a signal is sent. The GPS receiver measures how long it takes for the signal to arrive. Knowing the speed of light, it calculates the distance to each satellite. One distance? You are somewhere on a sphere centered on the satellite. 2 distances. You're somewhere on the circle where 2 spheres intersect. 3 distances, 2 possible points, one usually in space, the other on Earth. 4 satellites. Your exact position, X, Y, Z, and correction of your receiver's clock. In reality, GPS measures time, not distance directly. Atomic clocks, the beating heart of every satellite. Each GPS satellite contains several atomic clocks. Cesium, rubidium, hydrogen masers. Precision. Error of less than 1 second in a million years. An error of 1 microsecond, 1/1,000,000th of a second, would mean a 300-meter error in position on Earth. Clocks are regularly synchronized by ground control stations. Relativity, Einstein, and the need for corrections, both special and general relativity, directly affect how GPS works. Satellites travel fast, approximately 14,000 km/h, so their clocks run slower due to special relativity, time dilation from motion. But satellites are also in weaker gravity than on Earth, so their clocks run faster due to general relativity. The net result: satellite clocks run ahead by about 38 microseconds per day. Without corrections, GPS would be off by hundreds of kilometers every day. GPS is daily proof that Einstein's physics is not just theory, it's practical reality. How your GPS receiver calculates your location. The receiver finds satellites using their ephemeris data. It measures the arrival time of signals from each satellite. It calculates the distance, time x speed of light. It solves a system of 4 equations with 4 unknowns, x, y, z, t. The result? Your precise position and extremely accurate time. Accuracy, basic GPS, usually 315 meters under ideal conditions. DGPS RTK, with corrections even 1-2 centimeters. Errors caused by the atmosphere, ionosphere, troposphere, signal reflections, multipath, obstacles or receiver quality. Biggest challenges for GPS and how they're solved: atmospheric interference. Signals slow down or are distorted as they travel through various atmospheric layers. Multipath. Signals bounce off buildings, rocks, vehicles, causing errors. Obstructions. Dense forests, narrow city canyons, or indoors can block signals. Deliberate jamming. The military can jam GPS signals in conflict zones. Solutions. Advanced algorithms to detect and reject multipath errors. Multi-system receivers using GLONASS, Galileo, BeiDou. Differential GPS, DGPS. Ground stations broadcast correction data. Assisted GPS, AGPS. Phones download satellite data over the internet for faster fixes. Other global navigation satellite systems, GNSS, GLONASS, Russia. Fully operational, used as a backup or supplement to GPS. Galileo, EU. The European answer with very high accuracy. BeiDou, China. Global and rapidly growing. gnss, Japan. Naviki, India, regional systems. Most modern devices use signals from multiple systems, multi-GNSS, for greater accuracy and reliability. GPS in practice? Where is GPS used today? Cars, smartphones, sports watches, drones, airplanes, ships, agriculture, self-driving tractors, precision seeding, field mapping, construction and surveying, plotting land, laying railways, building bridges, power grid and finance, time synchronization, trading and network management, emergency services, locating people, precise 911 calls, disaster response, science, seismology, tectonic plate movement, glaciology, everyday life, finding your phone, tracking parcels, running apps. GPS myths and misconceptions. GPS works without satellites. No, receivers require satellite signals. Cell networks, AGPS, only help speed up the first fix. GPS is always accurate to a meter. No, accuracy depends on the number of visible satellites, receiver quality, obstructions, and weather. The military can turn off GPS. Technically, yes, or degrade accuracy during war, but it would have huge economic and safety impacts. The future of GPS and navigation centimeter-level accuracy for everyone, RTK, PPP, next-gen satellites, stronger signals, better anti-jamming integration with 5G, inertial sensors, cameras, AI autonomous vehicles, drones, robot science, climate research, wildlife tracking. GPS is the invisible backbone of our civilization. Without it, transport, rescue, science, banking, and even daily life would stop. Try turning off GPS for a day and see how much just stops working. Comment below. Has GPS ever saved you or sent you somewhere totally wrong? Like, subscribe, and share this video. In the next episode, what would really happen if GPS went down for a day? And could it actually happen?